Imagine standing at the edge of a gorge with a rope bridge, a flickering lantern, and a horde of mutant zombies closing in. 4 people need to cross, but the bridge holds only 2 at a time, and the lantern must accompany every crossing. Each person moves at a different speed: 1 minute, 2 minutes, 5 minutes, and 10 minutes. When 2 people cross together, they move at the slower person's pace. The zombies arrive in just over 17 minutes. At first glance, the math seems impossibly tight, always leaving the group a minute or 2 short. Yet a solution exists, and finding it reveals something profound about how the human brain navigates constraint. This scenario belongs to a legendary class of logic puzzles known as bridge and torch problems, which have circulated in computer science and mathematics education for decades. Research in cognitive science shows that these puzzles activate a specific mode of reasoning that resists our default mental shortcuts. The brain's first instinct is to pair the fastest person with each slower individual, ferrying everyone across one by one. That intuitive strategy feels efficient but fails under the time constraint. The real breakthrough demands a counterintuitive leap, pairing the 2 slowest people together. This is where constraint becomes a creative catalyst rather than a limitation. Studies in problem-solving psychology reveal that people consistently struggle with optimization puzzles precisely because the optimal path feels wasteful at intermediate steps, forcing reasoners to suppress greedy instincts in favor of global efficiency. The most natural approach to the bridge puzzle is what mathematicians and computer scientists call a greedy algorithm, a strategy that makes the locally optimal choice at each step. Send the fastest person back with the lantern every time, and shuttle each slower individual across one by one. It feels logical, it feels fast, and it fails. Under the greedy approach, the total crossing time sums to 19 minutes. 1 plus 1 plus 5 plus 1 plus 10, plus the return trips of the fastest runner. 2 minutes over the deadline means zombie dinner. Greedy algorithms are deeply embedded in human cognition. Research in behavioral economics and decision science demonstrates that people default to immediate optimization under pressure, a phenomenon sometimes called local hill climbing. The brain evaluates the next move in isolation, rather than computing the global cost of a sequence. Daniel Kahneman's framework of System 1 and System 2 thinking helps explain this. Fast, intuitive System 1 grabs the obvious pairing, while slow, deliberate System 2 must override that impulse to discover the better path. A 2023 study published in Cognition confirmed that when participants face multi-step optimization tasks, fewer than 30% spontaneously consider non-greedy strategies on their first attempt. The percentage rises dramatically, however, when solvers are explicitly encouraged to question their initial instincts. This finding underscores a broader principle in learning science. Awareness of one's own cognitive bias is often the single most important step toward solving hard problems. The elegant solution hinges on one insight that feels almost reckless. Send the 2 slowest people across the bridge at the same time. Here is the sequence that saves everyone. First, the 1 minute and 2 minute crossers go together, taking 2 minutes. Then the 1 minute crosser returns with the lantern, costing 1 minute, 3 minutes total so far. Next, the 5 minute and 10 minute crossers go together, taking 10 minutes. 13 minutes have now elapsed. The 2 minute crosser, waiting on the far side, grabs the lantern and runs back in 2 minutes. 15 minutes total. Finally, the 1 minute and 2 minute crossers dash across together one last time in 2 minutes. 17 minutes exactly. Everyone is safe. The magic lies in bundling the slowest pair. Because 2 people crossing together always move at the slower person's pace, pairing the 5 minute and 10 minute crossers wastes only 10 minutes rather than 15 if they cross separately. That 5 minute savings is the entire margin of survival. Research in operations, research in combinatorial optimization shows that this bundling principle scales to many real-world scheduling problems, from manufacturing assembly lines to operating room scheduling in hospitals. A 2022 analysis in the European Journal of Operational Research found that grouping slow tasks together and using fast agents for transitional steps reduced total completion times by up to 25% in simulated logistics networks. The bridge puzzle, in miniature, teaches the same lesson that industrial engineers spend careers mastering. Sometimes the best strategy is protecting your fastest resources for the errands nobody else should do. There is a peculiar emotional arc to solving this kind of puzzle. The correct answer, once revealed, seems almost embarrassingly simple. Yet before discovery, it feels invisible. This gap between difficulty and simplicity is not a personal failing, but a well-documented feature of human cognition called the insight barrier. Gestalt psychologists identified this phenomenon nearly a century ago, noting that certain problems require a restructuring of mental representation before the solution becomes accessible. Modern neuroscience has pinpointed the anterior superior temporal gyrus as a brain region that activates during these aha moments, essentially rewiring how a problem's elements are categorized. The bridge puzzle specifically triggers what cognitive scientists call functional fixedness, the tendency to see objects and agents only in their obvious roles. The fastest person seems like the natural shuttle driver for every trip. Reassigning that role to the second fastest person for one critical return trip requires breaking a mental frame. A 2024 study in psychological science found that training participants to deliberately swap roles and constraints in logic puzzles improved their insight problem-solving accuracy by 40% across unrelated tasks. This transfer effect suggests that practicing counterintuitive reasoning in one domain genuinely builds flexible thinking elsewhere. The bridge puzzle is not merely a party trick. It is a miniature gymnasium for the prefrontal cortex, strengthening the neural circuits responsible for cognitive flexibility, inhibitory control, and strategic planning, skills that research consistently links to academic achievement and professional adaptability. The lantern and bridge scenario may seem like a contrived thought experiment, but its underlying logic surfaces constantly in everyday decisions. Project managers face the same optimization challenge when scheduling team members with different skill speeds on sequential tasks. Parents encounter it when coordinating morning routines with children who move at wildly different paces. Even cooking a multi-dish meal involves bundling slow processes together and using fast intervals for quick preparations. The core principle remains identical. Identify your bottleneck, protect your fastest movers for transitional tasks, and resist the urge to optimize each step in isolation. Educational research increasingly supports using logic puzzles as pedagogical tools. A 2023 meta-analysis in Educational Psychology Review examined 41 studies and found that regular engagement with constraint-based puzzles improves students' mathematical reasoning scores by an average of 15%, with the strongest gains among learners who initially scored lowest. The puzzles work not because they teach formulas, but because they train the brain to hold multiple variables simultaneously and evaluate sequences holistically. This capacity, known as relational reasoning, is a cornerstone of scientific thinking. The next time a problem feels impossibly tight, with every obvious path falling just short, that frustration itself may be the most valuable signal. It means the greedy solution has been exhausted, and a deeper structural insight is waiting to emerge. The bridge is always crossable. The lantern just needs to be handed to someone unexpected. Thanks for watching. If you have anything to add, drop a comment below. Don't forget to like and subscribe for more videos exploring the world around us.